Hello and welcome back to Dr. Logic Awkwardly Does Logic. In this video, I would love to be able to prove to you that in S5, every formula is equivalent to something in ordered modal conjunctive normal form. However, it's going to be a lot easier if I don't do that now, but I first give you some definitions. More definitions, everybody loves a good definition. The definition I'm going to introduce you to today is that of modal degree, and it's a way of calculating essentially the modal complexity of a formula. So let's get up the whiteboard because we're going to want to see the details because this is going to be a counting argument. So the modal degree of a well-formed formula phi is going to be defined inductively. That means I will tell you what the modal degree of an atomic formula is, and then I will tell you how to calculate the degree of a more complex formula on the basis of the degree of the parts that go into that complex formula. So, point number one, the modal degree of an atomic proposition is 0, which makes sense because atomic propositions have no modalities in them, and modal degree is tracking the complexity of the modal part of the proposition. So that's all of our atomic propositions, completely non-modal, modal degree 0. Then, if we have some formula phi, which has modal degree n, then if you stick a negation on the front of it, not phi is also of degree n. This is because in kind of modern modal logic, negation isn't a modality. So if we add a negation to something, we haven't changed the modal degree. It's exactly the same as it was. If we have some formula phi, which is of modal degree n, and another formula phi, which is of modal degree m, might be bigger, might be smaller, might be the same, doesn't matter. We just have two formulas, and they each have a modal degree. Then the disjunction, the conjunction, or the implication between these two formulas will all be of degree max and m, which is just a fancy way of saying whichever the two is bigger, that's the modal degree that you have. So if phi is of degree 2 and psi is of degree 5, then phi or psi is of degree 5. Again, you haven't added any modal operators, so the number can't get any bigger than it already is, in a sense. So then, of course, we get to the interesting one, which is that if phi is of degree n, then box phi and diamond phi are both of degree n plus 1. So that's where we get our modal degree being added. So what we have here is a way of kind of taking a formula and unwrapping it or rewrapping it. You can either do it, there's many different ways that you can go about calculating it, but it's always going to be on the basis of where do the modal operators get added. So let's pick a formula, say P and Q, or possibly R implies necessarily possibly P and Q, or not R. Let's see. So it's very easy to calculate the modal degree of a particular formula just by building it up from the base down. So all of your atoms are going to be of degree 0, and then just look at each stage of the complexity of the formula. So not R, this is of the form not phi, so we look at number 2. If phi is of degree n, then not phi is of degree n. So Our phi here is r, it is of degree 0, so not r is of degree 0. P and q, phi is of degree n, psi is of degree m, then we take the maximum of then. The maximum of 0 and 0 is 0, so we have 0 here. Ooh, look, now we're adding a modal operator. If we have something of degree n, and then we add a diamond in front of it, we get n plus 1. So we are adding a diamond to something of degree 0, so this one becomes of degree 1. We add it again, we've got another modal operator, so that's degree 2, look at that. Now we've got a disjunction. It is a disjunction between something of degree 2 and something of degree 0. 2 is the bigger one, so here is a 2. Let's see, let's get the other one. So here we've got a 0 conjoined with a 0. So this is just going to be the maximum. That's another 0. Here we've got a 0, but we've stuck a modal operator on the front. So that becomes a 1. Then we have a 1 implies a 2. So this is of this case. So the maximum of that is 2. So there we go. And then we've got a 0 disjoined with a 2. So this one is going to be 2. So this entire modal formula has degree 2. Now, the thing to realize is that modal degree is not the same thing as the longest string of iterated modalities that you have. It is in this case because we've got 2 iterated modalities here, and we ended up with something that is of degree 2. Modal degree is a little bit more complex than that because you might have embedded modalities that aren't necessarily embedded in a strict string. So let's get rid of this so I can keep the definition up and still have a bit of space. And I want to draw. I like drawing. There we go. Consider this formula. We have possibly P and necessarily, possibly not, oops, I'll go with not P or R. There are no iterated modalities here, and yet this is going to have a fairly high modal degree because of the number of modalities that are embedded inside each other. So let's just run through this again real quickly. We label all of our atoms with 0, we build them up. So not P or not 0 becomes 0, possibly 0 becomes 1, 1 or 0 becomes 1, necessarily 1 is a 2, 0 and 2 is 2, possibly 2 is 3. So this one has modal degree 3, even though it doesn't have any iterated modalities. So what they have are what we can call bracketed modalities, in the sense that it's got one modal operator that is inside the brackets of another modal operator. So this is the definition. And next time I'm going to show you something super cool, which is that in S5, every formula is equivalent to a formula that has modal degree maximum 1. So you might have some of the most enormously complex modal formulas you'd ever think of, loads of embedded modalities, iterated modalities, all of these things going on. And yet we will be able to show in the system S5, you can prove that they will be equivalent to something that has at most a single modality without anything else embedded or underneath it or iterated in it. And if you're thinking back to ordered modal conjunctive normal form and what the bits of that look like, you'll begin to see why this will be such a useful thing that we'll use when we want to prove that every formula in S5 is equivalent to something in OMCNF. All right, join me next time and I'll show you how to do the reduction thing because it's super cool. Until then, take care. Bye.